Hello and welcome to our talk. There is this perception here, particularly down the infrastructure level, that most of the internet problems are now well and truly solved. We understand TCP, don't we? The same way we understand IP as well. We know this is just a set of solved problems. But in some ways, we do not. There is this curious interplay between TCP software and network hardware. In this research, we develop a novel two-lock RentSeeking based framework to analyze and design multipath TCP protocols. This is the outline for today's talk. TCP is an adaptive rate control algorithm. What it is trying to do right at the end that each system is to establish between the sender and the receiver how fast can the network transfer data packets. Multipath TCP allows user to split its traffic across multiple paths and improve reliability and aggregate throughput by aggregating the bandwidth of different paths. With the proliferation of mobile devices, there is growing number of folks that are physically able to use two or more network interfaces. However, these paths were rarely used earlier in the applications. With the standardization of multipath TCP, RFC6 at 2.4, the situation has changed dramatically. Using multipath TCP, a smartphone phone can use both Wi-Fi and cellular networks to exchange data. One of the important applications of multipath TCP could be future autonomous vehicles. Vehicular network could benefit from multipath TCP. For example, autonomous vehicles may need to send the 3D views of their environment to remote monitoring servers under extremely tight network network deadlines to ensure safe operations. So the most important use case of multipath TCP is the aggregation of bandwidth across different heterogeneous paths. This use case has been deployed on smartphones by telecom companies like Korean Telecom, where they allows combining 4G and Wi-Fi, and also in hybrid access network, where they allows combining ADSL and 4G. Last year only, 3GPP has adopted multipath TCP as the basis for their access traffic steering, switching, and splitting, what they call ATSSS, and helps to combine Wi-Fi and 5G for the aggregation of the bandwidth. What multipath TCP and TCP does, it actually works as a pacing protocol. If we think of network as a conveyor belt of packets, as the packets leave a network, we can put a new packet on, or think it as a freeway. When a car leaves a freeway, we can put another car on it, and if we do this just right, the freeway will never clog up. So how does TCP do rate adaptation? It starts with the ACK-based flow control, packet in and packet out as discussed earlier. But while there are no problems, in other words, when none of the packet get lost or clogged up in the path, it will gradually increase as its sending rate, because it knows the amount of time between the sender and the receiver, when what we call the round trip time. In a steady state, with everything going fine, it will put one packet on the network for each RTT. So slowly and surely TCP will increase as its rate. But the networks are not infinite, right? The network paths are not infinite. They have limited capacity. So at some point when we put that extra packet in, it won't get all the way through. It will land up in the buffer, which increases delay. But in another RTT, we are sending one more again. So the buffer starts filling more and more quickly, increasing delay more and more, and eventually becomes full. The buffering delay or the queuing delay is the main source of the delay, which could be managed intelligently by using smart pacing technique. In other words, it is worth observing here that TCP pacing rate determines the corresponding loss or delay along the network path. Network utility maximization for multipath TCP has been a challenging task since there is no well-defined utility functions for multipath TCP. In this paper, we identify the conditions under which we can use Kelly's network utility maximization mechanism and explicitly compute the equilibrium. We obtain this by using Tulloch's RentSeeking framework. Furthermore, this approach allows us to design MPTCP algorithm with common coupled delay and loss constraints at the subflow level. This utility function has a diagonalistic cavity which guarantees global unique normalized equilibrium as well. In addition to the theoretical analysis, we also conduct network emulation experiments to illustrate that our proposed MPTCP algorithm provides higher throughput, better robustness, and improved responsiveness compared to other existing MPTCP algorithms. Rent seeking is an economic concept that occurs when an entity seeks to gain added wealth without any reciprocal contribution to the productivity. Typically, it revolves around the government-funded social services and social service programs. It is based on the economic definition of rent, which is defined as the economic wealth obtained throughout the shared or mm, potentially manipulative use of resources. So our main insight here is to manipulate the existing resources in such a way that we can adopt Kelly's approach of transforming fairness problem into the game between TCP user shares that shares several features with that of rent-seeking framework. And the objective is again to aggregate the Wi-Fi and non-Wi-Fi 5G seamlessly by equalizing the delay across the paths. In coupled multipath TCP algorithm, in all existing algorithm, it is known that if one of the paths fails to meet the loss and delay constraint, then the subflows on the other path also suffer. Therefore, multipath TCP subflows context can be considered as a game with common couple constraints. In games with common couple constraints, when a player fails to achieve the constraints common to both players, all other players will also be penalized. Such games can therefore be viewed as cooperative in the objectives of meeting common constraints and non-cooperative in the context of utilities. We exploit rent-seeking framework for studying the context between subflows, thus providing insights in designing cooperative multipath TCP algorithm by balancing, equalizing the loss and delays across paths. We attain this by intelligently tuning the passing rate because we have observed that passing rate is the one that can determine the loss and delay in the network path. Such developed multipath TCP will be highly useful for autonomous vehicle, augmented reality, and virtual reality, including video streaming applications, because of its throughput intensive nature, low end-to-end delay, and guaranteed reliability nature as well. We have taken an example of multipath TCP LIA here just to illustrate the coupling mechanism across different paths in the existing algorithm. So the window increment mechanism is coupled based on the path delay and the loss characteristics using these windows and delays and leading to this coupling factor. But with our new insight, if we can balance the RTT across two heterogeneous paths, if we can equalize it, then the coupling factor will boils down to the fraction of their windows, which is actually the fraction of packets across different paths. That provides an important insight towards the definability of the utility function for multipath TCP itself. Here we have compared different versions of LIA and BALIA based on their window increment and window decrements parameters. But the main idea that we have here is this one here, where we are tuning the sending rate based on the increment in the window just by observing the instantaneous delay of the network and target delay for all of the network paths. So QI slowly converges towards the target delay D if we adopt these equations in the window evolution of RSF MPTCP. And this is the underlying utility function for the window mechanism that we have, which is taken directly from Tuluk's RentSeeking framework. And it's a concave function. Yeah. And with multiple multipath TCP sources, we can derive that the utility function for the nth MPTCP connection will follow this one. We have evaluated our MPTCP algorithm by comparing it with other three well-known algorithms, LIA, OLIA, and BALIA. This is the experimental setup that we have. The three algorithms, LIA, OLIA, and BALIA, are all available in the experimental Linux implementation. We use this Linux implementation as the basis for our experiment as well and modify it for RSF MPTCP. For the verification and validation of our experimental environment, we just started with two different baseline cases. So scenario one, where we just use single path for all MPTCP and regular TCP, and we observe that RSF performs same as that of TCP and BALIA in single path network. Then we investigate for the homogeneous path without any loss, and we also observe that RSF performs same as that of LIA in homogeneous path with no loss. Moving forward to different scenarios where we have summarized it here in the table. For homogeneous path, we observe that RSF MPTCP start to differentiate itself from other MPTCP and outperforms all other MPTCP in terms of throughput. It also achieved better fairness as we have compared with Gen Fairness Index. Another observation that we have is for the heterogeneous bandwidth path, and we observe that with heterogeneous bandwidth path, RSF MPTCP outperforms all other MPTCP algorithms and can exploit the heterogeneity of the bandwidth intelligently. Another observation that we have is the decrease in throughput with increasing delay of one of the paths. We observe that all MPTCP and the throughputs of all MPTCP decreases with increase in delay, but the decline is quite gradual in RSF and quite pronounced in other algorithms. Yeah, we have developed a novel framework for designing MPTCP algorithm using RentSeeking M theoretic framework, which guaranteed the existence of the utility function with strict diagonal concavity. Thank you very much for listening. Your queries and questions are warmly welcome.